All right, guys, welcome back. I hope you're all doing well. So, before we get started, any questions, concerns about anything before we move on? Okay, so if you don't have anything, let's get started with where we have left behind. So, what we will do is we'll do a quick recap of what we wanted to do in the last class, and then we'll continue from that where we ended. Okay, all right, so welcome back. So, in the last class, we did a small exercise. So just a quick recap, right? What we wanted to do really is to understand how data is represented in your devices, right? We have figured out that your smart device is smart because it can do multiple operations, multiple types of data processing, right? And we also came to a conclusion that the data that is presented at the very fundamental level, there is no really difference between the data that corresponds to, for example, music, data corresponding to video, and so on and so forth, right? Data itself, at the very fundamental level, the way it is stored in the device is identical. Just like, for example, in your brain, we took the analogy of the brain in the last class, right? Ultimately, all the signals that are going to your brain, to all of through all of your sensory inputs, your eyes, your ears, your sense of touch, and so on, at the level of the brain itself, all of these are electrical in nature, electronic pulses that are being propagated to your brain, and your brain basically makes sense of this. It basically gets propagated to the right section of the brain, and your brain makes sense of that information, of that stimulus, and forms an image if it's coming from your eye, uh, and so on and so forth. Okay, all right. Now, in exactly the same way, uh, at the fundamental level, data is identical. The way it is processed and being sent to the peripherals of your device, that changes everything, right? You basically hear sound, you see the video, and so on and so forth. Okay. Now we also undertook a simple exercise uh, to really understand how we can get there, how to really understand uh, how we can actually store data, right? So for that example, what we have looked into was, let's say I want to store a sound clip. So somebody is basically, singing, okay, and we wanted to basically uh, store that as a clip within my device, okay. And we have already seen that these are all electronic. Somehow these are all electronic signals. I want to store them as an electronic signal, as an electronic data, if you will, okay. And what we've realized is, first of all, if I want to do this, I need to have some kind of a device that can convert this sound. Again, sound is nothing but a pressure wave. It's a device that can convert that into an electronic signal in the first place, right? So that device that we use in its most general term, that is called the transducer. In this case, we want basically a mechanical transducer or electronic transducer that can convert these mechanical uh, vibrations, right? Your basically your speech is nothing but a pressure wave that is established in the air. The air molecules, move around and basically establishes this pressure wave that propagates and then strikes this transducer, and this transducer converts that vibration into an electronic signal, a signal that's continuously varying with time. Right? This is what we've seen. A signal that continuously varies with time, and that's electronic in nature. That's your voltage. So we are using this transducer to convert that speech into a voltage signal. Okay. Exactly. So a microphone is an example of a transducer. That's absolutely correct. Now, I can also produce a transducer, like a similar transducer, using a simple capacitor, right? We have two capacitor plates. If I fix one of the plate, okay, and that's the fixed plate, and let's say this is a movable plate. So let's say this is your diaphragm, if you will. And let's say I incorporate this capacitor in a simple resistor network, basically simple RC network that is powered by, let's say, a DC voltage source, okay? And I'm measuring the voltage across the resistor, or it can be voltage across the capacitor, doesn't matter. So what you have, once these pressure waves impinge on this movable plate or the diaphragm of the capacitor, that plate moves, changing the distance between the two plates, right? So in other words, the capacitance changes, and because of the capacitance change, the voltage across the resistor is going to be, I'm going to get a wave that corresponds to how this voltage across the capacitance is being changed upon impinging of these air molecules or the pressure wave on the capacitor plates. So a transducer can be built in multiple different ways. Yes, a microphone is a transducer. Okay, now the next thing that we wanted to do, we realized that even if it's a very short speech segment, if it's a continuously varying signal, then I need to deal with infinite number of points. That's something so that means if I want to store all of those points, I need infinite amount of memory to store a simple speech signal. And that's not really feasible, right? So the next thing that we need to do is to just collect, instead of having a continuously varying signal, just collect some points, okay, from that signal, so that in a way that I will be able to reproduce that signal without losing any information content in that signal. Okay, all right. So that's what we have done in the last class. So what we have, and the process of doing that is basically called sampling. So in effect, what we're trying to do here is we're trying to take a continuously varying signal and make it discrete, right? So instead of that, we are basically capturing the signal at discrete intervals of time. So now I can basically work with a finite amount of samples. Okay, and I don't really need to have an infinite amount of memory to be able to actually store these samples. Okay, now the other thing that we noticed, so of course again we discussed the criteria, the Nyquist criteria to be able to do this, so my information content is not lost during the sampling, right? So as long as you adhere to those principles, you don't really lose any information content during this process. Now the idea now is to basically, if I want to store this just as at the intuitive level, what we are trying to do here is basically you have these nodes in your circuit, in your device, okay, and each node voltage can be adjusted to the voltage of each of these samples, right? If I'm able to do that, then I'll be able to store that signal or the speech segment or the sound segment in my device by having each node voltage corresponding to the voltage of each sample. Okay, and we realize that, again, let's say I have my transducer designed so that it will produce an output between 0 volts and a maximum of 5 volts. So that's the maximum it can go. Okay. All right. Now you will see that because this signal can be anything, right? My voltage value that I measure can be continuously varying between 0 and 5 volts. So I need to have some kind of mechanism by which I can come to each node and adjust the voltage of each of these nodes to correspond to these continuously varying values of my samples, and which is not a trivial undertaking. We have to be, we don't really have the means, again, especially now we are talking about, so much of data, so many songs and videos that we want to store. It's really not possible by this approach. Okay, so we have to come up with another scheme, come up with an improvement over this, make our life easier, or to make the life of the designers easier. So the next step that we wanted to do was to do what is called a quantization. Quantization, just like we have gone from an infinite amount of data to finite amount of data by using sampling, we can also quantize along the y-axis Okay, so that now going from infinite amount of variations in the data that you may encounter, you will be going from infinite to finite amount of data variations or the sample variations that you can have. Okay, and the way I will do that is you sample it, you quantize it. So what do I mean by quantization? So that's 0 volts to 5 volts. I'm basically dividing this axis, the y-axis, into discrete amount of possible values. Okay, very similar to what we have done on the x-axis sampling. I'm doing it on the y-axis to get a finite amount of variations in my sample values. Okay, now let's take this example here. So this particular, let's say this is level 0, level, let's say some n, arbitrary n, and level n plus 1. So if I just zoom it up, what I have is basically 2 levels, all right? And my sample is basically lying something like this. So that's level n, n plus 1. So if my sample is lying, let's say, closer to n plus 1, I would formulate a rule so that this particular sample, this sample I, is assigned level n plus 1, okay? A voltage corresponding to level n plus 1. I hope that makes sense. So now, going back to my device, in each of my nodes, now I'm working with finite amount of variations. So let's say this is my level sample I here, this particular node corresponding to this sample I. I just have to tune the voltage or make the voltage of this node to be, to be that corresponding to level n plus 1. And so on, and I will repeat the process for every other node. Okay. All right. So that's quantization, going from infinite amount of variations to finite amount of variations in my sample values. Okay. Now, even with that improvement, that's a big improvement. But even with that improvement, it's really not trivial. We don't have an electronic component that would allow me to do that easily across billions of these nodes. Okay. We just don't have that yet. Maybe in the future we may have that technology, but right now we don't. Okay. Now, but what we do have is, again going back to the lecture, what we do have is this very interesting device called the transistor. Okay. Transistor. Again, you can use this for multiple applications. You can use this as an amplifier for your music systems, for example. You can also use this as a switch. And for this particular, for the technology that relies on, for the technology that's made for computations, we use this as a switch. Okay. So what you have is basically a simple way, and I can, as I mentioned before, now with the technologies, these transistors can be made so that they rely on the substrate, like a silicon, like a material properties, to make them. And the less of amount of material I can use, the more transistors I can fit on the same same wafer, and the cost goes down, the functionality goes up by doing that, and over the many years we have been able to actually build or fabricate billions of these transistors on a single wafer. Okay, so the efficiency is very high in terms of fabrication. So that's the switch. Okay, what it can do is, for example, let's say you have, let's say this is 5 volts. Just to give you an example, let's say this is my transistor switch. I can operate that switch electronically. I can close it, open it by electronic means. At this time, just that's what you need to know. And let's say this is my resistor, okay, and that's ground. A simple circuit, a simple resistor that can be switched. And let's say this is the node I'm talking about. Let's say this is my node. Now I can control the voltage at this node to be either 5 volts. How do I control it to 5 volts? Basically, if I turn on this switch, it's turned on, okay, the voltage at this node would be 5 volts, right? Or that's one possibility, that's turned on, the switch turned on. If I turn off the switch, if I just open the switch, Now this is disconnected from this 5-volt supply. The voltage at this node will be 0 volts or ground, right? That's turned off. Now I can make these switches in billions easily on the same wafer. Okay. So if I can actually use these switches to represent my levels, then I'm up to something, right? Now, but the challenge is we only have 2 levels, right? When I use these kind of switches, each of this node, which we talked about in the just a few minutes back, right? Each of these nodes can only have 2 levels, level 0 and level 1, right? Again, if you notice, this is my signal, and if I'm dividing my, if I'm quantizing my signal, 5 volts, how do I, again, one thing you have to remember, and one thing you can directly notice is when I'm assigning these samples to these levels, I am losing some actual sample content, right? I'm introducing some error into my measurement. Do you see that? By having this sample, and where is that error? Because my actual sample is here, but I'm basically assigning this sample to this level, which is here. So there is some difference between this sample and this level, and that's my error. That's also called the quantization error, because you inevitably introduce that error, the quantization error. How do I minimize it? How do I minimize the quantization error here? I will minimize it if I can reduce this discrepancy, right? Yeah, I can minimize it if I have more number of these quantization levels, right? The larger, the more number of these levels, the error will be smaller, right? The more the levels, the error will be smaller. Now, but by using this mechanism with the switch, I can only have 2 levels per node. It's like saying, okay, between 0 and 5 volts, I will only have basically 2 levels. And obviously, that's not the way we need to do it, right? So what do we do then? If I want to get, let's say, with this transistor switch, I want to get 4 levels. How do I do this? What I can do is use 2 nodes to represent a level. So 2 nodes combined would represent 1 level. Can I do that? I can do that. I can make my transistors to be extremely small. I can have billions of these, so that's fine. I can use 2 to make 4 two nodes to represent 1 level. How do I do this? Simple, right? So let's say these are my 2 nodes. Okay. Now I can I can assign 5 volts to, let's say, I call this level 1. 0 volts, I will call this level 0. You can also think about as a logical level 1, logical level 0. Okay. So now I can encode my level 0. Okay, when I say level 0 here, I'm talking about these levels. Okay, these levels. Let's say I have, in my hypothetical situation, I'm basically having just 4 levels: 0, 1, 2, 0, 1, 2, 3, 4 levels. Okay. So this is my level 0, level 1, level 1, level 2, level 3. So my quantization process gave me 4 levels. So level 0, I can represent this as both node voltages 0. I can call that level 0. Both node voltages to be one of the node voltage to be 1 or 5 volts. I will call that level 1. 1 0, I will call this level 2. 1 1, I call this level 3. So by combining nodes, I can get multiple levels. Okay, can I get more than this? Again, level 4 levels is nothing, right? It's again you're going to have a large uh, quantization error. I would like to have multiple levels. I would like to have like 200 levels or something. How do I do this? Just use multiple nodes to represent your levels. The larger the number of nodes, the more the number of nodes you use, the larger the number of levels you will have, right? And that basically brings down, so what I've just represented here is nothing but binary. It's a binary representation. We're already talking about base 2. And this makes our life easier because your transistors can be designed, can be fabricated in billions, and I can apply them and in more efficient uh, design principles. Okay. So now that brings us to the justification of why we want to re-examine other number systems. Of course, we are comfortable with decimal number systems, but applying decimal directly into device design is not the most efficient solution at this time, unless we come up with a device just like what we come up with, right? We have a transistor that can do 2 levels. If I can come up with a device that can have like 10 different levels, 10 different states, if you will, then yes, I can basically have everything in terms of decimal. All my data can be in terms of decimal representation. We don't have such a device yet, so we have to rely on the transistor and this way of thinking through things. Okay, let me pause here and let me see if you have any questions before we move on and start reviewing the number systems. Any questions on anything, on the conceptual understanding? Again, I wanted to approach this on an intuitive level, okay, something that you can connect to. Okay, what do the ones and zeros means on the nodes? Okay, so in this case, the 0 would be 0 volts. In the way we have described this problem, the 1 would be corresponding to 5 volts. So when I see a 5 volts on a node, that corresponds to a logical 1. When I see a 0 on the node, that corresponds to 0, value of 0. Okay. And how do I get there? I can simply get this by turning on or off the transistor. So this is the way. So these are my nodes in my circuit, and each of this node is connected to this transistor, to this circuit in this way, again intuitively. And by turning on the transistor, I can control this node to be at level 1. Turning off the transistor, I can control the node voltage here to be at 0 volts or 0 level. Okay. So I can do 1 or 0 at this node simply by turning on or off the transistor. And I can do that through electronic means, because this transistor is nothing but an electronically controlled switch, if you think about it. Okay, so I can send an electronic signal to control it to be on or off. That's absolutely right. Okay, that's a very good question. Does it have to be a 5 volts? No. When the technology evolves, of course, right now, the voltage for this has been reduced to be even 1.1 volts or so. Okay, the idea is we want to be able to distinguish between 0 and 1. Okay, and over time we have made that improvements, because again, when you have noise that is acting on your signal, then your system it may be difficult for your system to distinguish between 0 and 1 level. Okay, so the answer is, so the question was, does it have to be 5 volts? No, it doesn't have to be 5 volts. In fact, right now we are looking at 1.1 volts or so to be level 1, 0 volts to be level 0. Okay, and because we have better signal conditioning circuits that can be used to distinguish and eliminate the noise. Okay, there's another question. Let me see what you have there. Okay, so your question, Julia, is when we are quantizing the space between the different levels. Again, we need to formulate a rule. So basically, what you're saying is, let's say this is your signal. These are your levels. That is the signal is between two levels I and I plus 1. how do I assign this to I plus 1 or I, right? Is that what it is? Okay. So again, that's I don't want to go into too much details in here, but that's something that your let's see, your analog to digital converter actually does it for you. Okay, so you have a rule that basically follows that rule, and basically assigns this to the right level depending on how close it is to that level. Okay, but if you want more information on that, I would suggest that you read a little bit about the analog to digital conversion process and the quantization process. Of course, that's not the emphasis of our course here, so that's why I don't want to get into too much details there. I hope that makes sense. But basically, you assign that rule to the quantization process, and that will basically take it. Okay. All right. Any other questions? Very good questions, by the way. Very relevant questions. Okay. So now you know the importance of going back and reviewing your concepts on the number systems, right? So let's actually start doing that, because we need the binary. You need the binary to be able to do all the things that your devices are doing currently, to be able to understand how everything works. So that's where we start, in being able to turn a dead looking device into something that can do marvelous things. Okay. All right. So number systems. Again, this is something that you must have already done. So it's not like I'm teaching you something new here. Okay. So let's start with the very basics. Something that you're kind of use it on a daily basis. Your decimal number system. Everybody uses it, I'm sure. And let's actually examine the nuances in this system. Okay, just try to go back and look at it in a magnified with a magnifying glass, if you will. So that's your decimal number system. We all know that the base corresponding to this system is 10, right? So that's base 10. You have 10 different, or let me call that unique, coefficients or digits or coefficients, because I use them interchangeably. Coefficients base 10, and you know already what are those. So you have 0, 1. These are all unique digits that you have all the way till 9. So you have 10 unique coefficients or 10 unique digits that goes with the decimal number system. Okay. If I want to get a number larger than 9, I would start using 2 digits, right? And so on. So that's that. And we also know that a number that is represented in decimal, 3 to 9, for example. Okay. The actual value of that is, you have basically 3 hundredths in that number, right? 3 hundredths. You have 2 tenths in that number, and 9 ones in that number. In other words, when you have a multi-digit number like this, each position of these digits an explicit and what do we call a weight is a specific weight is associated for each of these digits based on the position of that digits, right? So the weight is implicit. 10 power 0 for the 9. Yeah, that's correct. Sorry, that's 10 power 0. Yeah. And if I want to get the value, that's what it is. And because I don't want to represent decimal numbers in this way all the time, that's too cumbersome, we basically take the digits, and the weights associated with this digit are implicit in the way these digits are arranged. Right? That's something that we already know. Okay. Now let's look at other number systems that are relevant to this class. Okay. Now we'll be mostly focusing on base 8, base 16, and base 2, of course. That's your binary, right? Base 2, again, all parts of 2, right? So that will be hexadecimal. Base 16, that will be your octal. Base 8. Okay, so let's examine them similar to how we have done for the decimal, summarize them, and then look at how do we convert from one base to the other, and so on and so forth. So let's look at base 8. Base 8, so of course that's our octal, base 8. So similar to what we have seen for decimal, we have 8 unique coefficients, 8 unique digits for base 8, right? All the way from 0. So these will be 0, 1, 2, 3, 4, 5, 6, and 7. So I have 8 unique digits or coefficients. And a number in base 8 would be something like this. A possible number will be 3 to 7. Right? Now, if I'm representing a number that is not base 10, then I have to explicitly state the base. Okay, because I'm trying to state that this is base 8, then I have to explicitly state that this is base 8. So I would do that using this format. Okay, so that's 3 to 7 base 8. And if I want to know the value of this, I would expand it, okay, and compute the value, right? So that will be 3. Again, similar to what we have seen for the decimal, each of the digits, the position of the digits, and a weight is associated with that, with depending on the position of these digits, right? Now, so what kind of weights? Again, for 3 you have 7 squared. Sorry, 8 squared, because that's base 8. So that's the weight associated with this. So you basically start with the first digit as the 0th position, the first position, the second position, and then you basically expand it by powers of that base. That's 8 squared plus 2 times 8 to the 1 plus 7 times 8 to the 0. So that will be so computing this sum would give you the value of this particular number in base 8. And of course, when you compute this, what you get is a number in decimal. Because we are more familiar with decimal numbers, we know, but just by looking at a number, we know what the value of that number is. By computing this particular expression, I will get the corresponding number in decimal, or the equivalent number corresponding to this number in decimal. Okay. The scientific notation is the same as decimal, but instead of 10, you put 8. That's correct. So, so depending on the base, you use the right base to expand the numbers. Okay. So in this case, you basically replace 10 with 8. That's correct. All right. So that's base 8. Let's look at base 16 now. Or hexadecimal. Hexa is 6, decimal is 10. So that's 16. Okay. All right. So what will I have now? So that's base 16. Now I need 16, because it's base 16. I have 16 unique coefficients or unique digits in this particular base. Unique coefficients or digits. So what do I have here? I'll have 0, 1, 2, 9. So that makes it 10 unique. Now what do I do next? With numbers I'm exhausted, right? That's the max. 9 is the maximum digit I can have. Now for the rest of the digits, the rest of the coefficients, I go A, B, C. I basically use the alphabets, E, and F. So that makes it 16. So I have 16 unique digits. A number in hexadecimal, an example of a number could be ABE7. That's a valid number in hexadecimal. Again, I have to specify the base because that's a number that is not decimal. I have to explicitly state what the base of that number is. ABE7, let's say 16. And if I want to know the value of that, okay, what would that value be? Again, I expand it. I expand the digits and compute the value, right? So that will be A. Again, the value of this digit A, because it comes after 9, is 10. Right? That's the value of this. B, correspondingly, B would be 11, C would be 12, D is 13, E is 14, F is 15. So here I can expand it. So that's my 0th position, first, second, third. So the weight associated with the A, that will be 10 times 60, base is 16, 16 cubed, right? That's the weight associated with this particular digit, plus B would be 11 times 16 squared. E would be 14 times 16 to the 1 plus 7 times 16 to the 0. So by computing this value, I'll get the corresponding decimal value of this hexadecimal number. So we know how to convert from an arbitrary base to decimal, right? All I have to do is basically expand it in terms of the base, apply the right weights, the right exponents, and I get the corresponding number in decimal. So that's base 16. Okay. And now let's examine base 2. Base 2 is simple because it's binary. I can only have 2 unique coefficients, so that will be 0 and 1, right? So let's actually do base 2. 2, that will be binary. I have 2 unique coefficients or digits, that will be 0 and 1. That's it. And a possible number in base 2 or binary, so it can be 1, 0. Again, I have to specify the base, and if I want to know the corresponding decimal value, just apply the right weights. That's your 0th position, 1, second, third, and 4th position. Apply the right weight corresponding to the position. That will be 1 times 2 to the 4 plus 0 times 2 cubed plus 1 times 2 squared plus 1 times 2 to the 1 plus 0 times 2 to the 0. Computing that value gives me the corresponding decimal value of that, or the equivalent decimal value of this binary number. Okay. All right. So far so good. I think this is something that you must have seen way back in school. So just I'm hoping that this will be a refresher of what you already know. All right, so that's base 2. Now let's look at, so far we have seen, and let's actually generalize this now. In general, so I want to just adopt this to any base. Let's say in general for base R. So for some arbitrary base R. Okay. How many coefficients would I have? How many unique coefficients or digits would I have? I would have R unique coefficients, right? Like for base 10, I had 10 unique coefficients or digits. For base 8, I had 8 unique coefficients or digits. For base R, I would have R unique coefficients or digits. R. I would have R unique coefficient or digits. Let me call them, you know, again, that's going to be 1, 2, 3. Again, depending on how large your R is, so those are your coefficients. So I will have R number of these. Let's say a number in base R could be something like, let's say an n-digit number would be something like an minus 1. So these are the coefficients. These can take any of these values. An minus 2, an minus 3, so on. A2, a1, a0. So that's a number in base R. If I want to know the value of that, if I want to convert that to the corresponding decimal value, again, I apply the right weights. I know the positions of these are already kind of here in these subscripts. I can basically expand this as an minus 1 times, apply the right weight in terms of the base. So that will be R to the n minus 1 plus an minus 2, R to the n minus 2, plus so on, a2 times R squared plus a1 times R to the 1 plus a0 times R to the 0. And by computing that expression, I would get the corresponding weight in decimal, corresponding number in decimal, right? All right, so that's for a general base, okay? Now what I want to do is, how do I convert a given number in decimal, for example, to the corresponding binary value? Let's start that, because again, that's an important thing. You need to be able to know how to do this. Okay? So we want to go from a decimal value decimal to binary conversion. Okay. Let's say your number is 262. That's your decimal. I want to know what the corresponding, if I want to convert that into corresponding binary value, what would that binary value be? Okay. And this is the approach. Again, there are multiple ways to do this. Let me show you the basic, the straightforward way. May not be the most effective way, efficient way to do it, but let's start with the straightforward way, and then we'll also look at, later on, we'll also look at how do we make it quicker, how do we actually convert them faster. Okay, and this particular technique is called the successive division technique. So what you do by division by base, and this is applicable not only for binary. If you want to convert a decimal value to any other base, for base 8, you can adopt the same technique to do that. Okay, so this is what I will do. So I have 262. What I will do is I will keep on dividing this, and by the base. In this case, base is 2. I want to divide 262 by base 2. I write the quotient here and the remainder here of the division process. Okay. Now if I divide 262 by 2, what I will get? The quotient will be 131, right? And the remainder here is 0. I don't have a remainder. Now I got 131. I'll divide that by 2. So that will be 65. Okay. Now the remainder is 1, right? Divide 65 by 2. So that will be 32. The remainder is 1. Divide 32 by 2. That will be 16. The remainder is 0. Divide 16 by 2, that will be 8. Remainder is 0. 8 by 2 is 4. Remainder is 0. 4 by 2 is 2. Remainder is 0. 2 by 2 is 1. Remainder is 0. And you will do it until you get a quotient of 0. In this case, 1 by 2 is 0. The quotient is 0. The remainder is 1. So you're basically decomposing your original number all the way down until you get the quotient of 0. Okay, and then you read the number from the in this way. So your binary code, the corresponding binary value would be, so that will be your, okay, let me see, let me just write this down and we'll describe what that means. So let me see how many zeros I have. 1, 2, 3, 4, 5, 2, 3, 4, 5, and then 1, 1, 0. Okay. All right. And that's the corresponding binary value of 262 base 10 will be 100000110 in base 2. And you will see that if I apply the right weight to each of my coefficients and find the value of this, you will see that that basically brings you down or gets you back your 262. Before I forget, if I'm given a number 262, let's say in base 8, I cannot call it 262 anymore. Okay, I have to call this 262 base 8. 262 corresponds to a decimal representation because I have 260 and 2, right? So that's more that corresponds to decimal. But when I'm for any other base, you have to basically spell out those each individual digit. So that will be 262 base 8. Okay. Now, because the leftmost bit, this one, has the highest weight associated all the time, right? This is the highest weight because I apply that because that's, you know, if you think about it, that has the highest value associated with it. So we will call that the most significant bit, the most significant digit or bit. In binary, when we're talking about binary digits, binary digits are also called bits. Okay, so that will be the most significant bit, or MSB for short. MSB, the most significant bit. The rightmost bit, the 0 in this case, in this particular bit, because that has the least amount of weight associated with it, we'll call that the least significant bit. Or LSB. Basically, digits in binary are called bits. Each digit is called a bit. So we'll use that convention. Okay. All right. So because we'll be dealing with this so much, it's a good idea that you get to know what are the first, at least what are the first 16, what are the first 15 binary numbers. You should be able to, just by looking at binary sequence, you should be able to know what the value of that is, at least for the first 15 binary numbers. That's very important because we'll be using it over and over again. And that will make your life easier once you actually know it. Okay, so that's how I would do this when I'm doing this for base 2. And I can repeat the process if I want to convert that into base 8. It's the exact same procedure. There's nothing different. All I have to do is divide it by that base. So in this case, instead of dividing by 2, if I want to convert that to base 8, I would divide this by 8 successively. Write down the quotient here, the remainder here, and then once I'm done, once I get a 0 as my quotient, then I would start reading it from the bottom to the top. The bottom digit would be your most significant digit or most significant bit, and the topmost would be your least significant digit or the least significant bit. That's the only difference. So let's do it for 8 as another example. So I divide 262 by 8. What do I get? So that goes 3 times, 1 time, right? And what is the remainder here? That's 22, 16, 6. Okay. And then 31 divided by 8. 8, is it right? No, is 2. Right? 262 divided by 8. The quotient is 32. The remainder is 6. That will be 4. The remainder is 0. That will be 0. The remainder is 4. Right? That's it. So for base 8, my 262 base 10 is equal to, again I read it from bottom to the top, 406 base 8. Same procedure, just the base has changed. That's the only difference. Okay. All right. What else do we need to know? So that's good. Later on, I will teach you another way of doing this much quicker, of converting a decimal value into the corresponding binary value. Okay. So this, of course, this works. There is nothing wrong with it. If you want to adopt it, use it, that's fine. But you still have to do that math, right? There is a better way to do it. All right. Now, and if I want to convert to 16, same procedure. All I have to do is divide it by 16 and write down the quotient, remainder, and you get that conversion. Okay. What else? That's good. Yeah. How do I convert? And this is important too. And that's why it's very important that you know the other technique too that can actually give you the answer more quickly, especially for binary. For converting from decimal to binary using the faster way would be actually very helpful. Now, given a binary number, let's say I want to convert from binary to octal or from binary to hexadecimal. And the process itself is actually very easy. Now, if you notice, my base 8 is really base 2 cubed, right? Base 8 is nothing but base 2 cubed. Base 16 is base 2 to the 16, 2 to the 4, right? Really, that's the same thing. So my base 8 and base 16 are basically powers of 2. All right. So if I'm given a number, let's say 1001, 1100, that's an 8-bit number. That's binary, base 2. That's an 8-bit number. 1 is the most significant bit. 0 is the least significant bit. And what I want to do now, I want to convert that to the corresponding octal. To be able to do that, I don't have to convert this to decimal value first, and then followed by the successive division to convert into octal. Okay, I can directly do it because of the fact that base 8 is 2 cubed. So all I have to do is I need to going from right to left. Okay, going from right to left, from the least significant bit to the most significant bit. I just group these bits into groups of 3s. So that's one grouping. That's one grouping. I don't have 3 bits here, so what I can do is I can just add 1 0 here. That doesn't add value to it anyway. Add a 0, so it doesn't matter. Just like in your decimal systems, and I will group this into 3. Okay, and then find the value of each of these grouping. Now, starting with 100, the value of that would be what? Again, you apply the right weights to each of these bits or digits. In this case, that will be 1 times 2 squared, right? That's the 0th position, worst position, second position, plus 0, plus 0. So that's nothing but 4. So that corresponds to 4. Okay. Likewise, I will do it for every grouping of 3s, right? So 0, 1, 1. What would that be? The value of 0, 1, 1 will be 3. Yeah, that's 2 plus 1, 3. And likewise 0, 1, 0. Apply the right weight, that's 2. So in other words, my corresponding octal number is 2, 3, 4, is 8. So I don't have to go through that intermediate step of finding the decimal equivalent first, then converting that decimal equivalent into octal by the successive division. I can directly go from the binary to the octal representation. Going along the same theme, I can also convert that into hexadecimal. Again, now you can get the hint, right? Group. No, in this case, again, this is something different, right? I'm not doing the successive division here. So here, I don't have to read it as 432. In this case, basically I read this grouping, corresponding value, and read it this exact same way. Okay. All right. Now, if I want to convert that to hexadecimal, same principle. Hexadecimal is again a power of 2. Is 2 power 4 is 16. Right? So in this case, I would again, starting from the least significant bit to the most significant bit, I will start grouping into 4s. Groups of 4s. I don't need, in this case, I don't need another 0 here. Groups of 4s. Okay. All right. So what is 1, 1, 0, 0? Now again, you write down the value of that. So 1, 1, 0, 0. You apply the right weights to the digits. So in this case, that's 0, 1, 2, 3. Right? That will be 1 times 2 cubed plus 1 times 2 squared plus 0 plus 0. Again, you have the weights, but that's 0 anyway, so it doesn't matter. So that's 8 plus 4, that's 12. The value of this is 12. However, again, remember that we are trying to convert that into hexadecimal. What does 12 correspond to? What digit does 12 correspond to in hexadecimal? 12 corresponds to C. That would be C. You do the same thing for 1001. Find the value of that. That's 8 plus 1. That's 9. So you're 9C. So the corresponding hexadecimal value would be 9C. Yeah, perfect. All right. So that's good. Now this is, again, as I mentioned, let me write down the value so that you don't have to compute this every time, especially for the binary 4-bit binary numbers. You need to be able to know just by looking at the numbers. So 0, 0, 0, 0 would be 0. 0, 0, 0, 1 would be a value of 1. 0, 0, 1, 0 would correspond to a value of 2. 0, 0, 1, 1 would be 3. That's 1. 2 plus 0 is 2. 2 plus 1 is 3. 0, 1, 0, 0. That's 2 squared plus 0 plus 0 is 4. 0, 1, 0, 1. 2 squared plus 1 is 5. 0, 1, 1, 0 is 6. 0, 1, 1, 1 is 7. 4 plus 2 plus 1, 7. 1, 0, 0, 0 is 8. 1, 0, 0, 1 is 9. 1, 0, 1, 0 is 10. It's 10. 1, 0, 1, 1 is 11. 1, 0, 1, 1, 0, 0. That's 8 plus 4, 12. 1, 1, 0, 1 is 13. 1, 1, 1, 0 is 14. And 1, 1, 1, 1 is 15. So you should be familiar with these binary values, and you should be able to instantaneously know what those values represent, what those numbers represent in value. Okay. Now, if I were to do this process, let's say going back to the same example, right? 232. Another way of doing things. Base 10, I would like to convert that to base 2, the binary value. How do I do this? One way is, of course, through the successive division. Can I do this in a more faster way? The way I will do that is I will first take 2 and raise 2 to a power that would give me a value closest to 232. So what should I raise 2 to a value that is closer to 232 but not exceeding 232? What would that be? What should I raise 2? Again, 2 power, let's say 2 power 4 is 16. Okay, to the 7, let's see. 2 to the 5 is 32. 2 to the 6 is 64. 2 to the 7 is 128. 2 to the 8 is 256. So 256 is larger than 232. So I have to stop here. I have to stop at 2 power 7. Okay. All right. So the idea is we will try to decompose this number in terms of the powers of 2. Okay. So that's the idea. All right. Now 2 power 7 is 128. 232. How much should I, so that I can write this? So what I'm trying to do here is I'm trying to write 232 base 10 as sum of powers of 2. That's my idea. That's what I'm trying to do here. So I can write this as 2 power 7 plus something, right? Plus something. What would that be? So what I would do is I would subtract 128 or 232, 128 from 232. What would that be? 232, because that's how much I need to account for as the balance, right? So that will be what? 4, that is 0. That's 1. So that's 104. Again, I would raise 2 to a power that will give me a value closest to 104 but not exceeding it. And I can see that that will be 2 power 6. So 2 power 6 gives me 64. 64. Right? So what is the balance I have to account for? That will be 0. That will be 4. I still have to account for 40. Okay. Again, I raise 2 to a power that will be giving me a value closest to 40 but not larger than that. That will be 2 power 5. Yep, 2 power 5. Okay. I'm doing it to 7. Which gives me 32. Okay. 32. That will give me 8. Right. That's 2 cubed. Okay, just double check if I did any computational numerical mistake. You just want to make sure that it is correct. 2 power 7 is 128. 232 minus 128 is 104. That's 4. Okay, that's 0. That's 104. 64 is 40. Okay, that seems like right. So in other words, my 232, I hope you have this already. I'm writing this in terms of powers of 2. So that's, I can, that's 2 power 7 plus 2 power 6 plus 2 power 5 plus 2 cubed. Right? Or I can write this as 1 times 2 power 7 plus 1 times 2 power 6 plus 1 times 2 power 5. Again, these steps you can easily skip when you're actually doing it, but just to illustrate how we are getting it, I'm just trying to put all the steps down. Okay, plus 1 plus 0, because I don't have a 2 power 4, can write this, the exponent could be 0, or that the factor can be 0, plus 1 times 2 cubed, because I do have a 2 cubed in my expression, plus 0 times 2 to the 2 squared, plus 0 times 2 to the 1, plus 0 times 2 to the 0. Okay, so now all I have to do is just pick the exponent, pick the coefficients, or these values, right, and put them down as a binary value. So what I have is 1, 1, 1, 0, 1, 0, 0, 0, base 2. Okay. So instead of doing the successive division, I can do this. Any questions on this? Is that right? Is that the one that we got last time? 232? Do you recall from your notes? Is that what we got for the 232 binary? Okay. So, 262. Okay, that's fine. Sorry, I was thinking 232 to compare, but thank you for the confirmation. All right, so that seems like it's correct. Does the method work? That's a good question. I have not tried it for another base, but I'm sure you can adopt it for another base. It's going to be a little bit more complicated, and I would not do that anyway, right? Because if I can get the binary quickly, because the only other bases, at least for this class, I'm interested in is the base 8 and base 16, and then all I have to do is basically group them right into the right number of bits and take the value. But that's a good question. You should be able to do it. It's not going to be as straightforward as binary. That's all I can say. But it's possible. Because now for base 8, the coefficients can range from 0 to 7. So it's going to be a little bit more complicated, not as direct as this. All right. What else? So let's now start looking at with how we actually do computations in different bases. Okay, so now we know how to convert, and I would recommend that you use the other technique, the one we just did, expressing a number in powers of 2 and trying to get that and trying to get the binary representation from that powers of 2 expansion. Okay, for the binary conversion, from decimal to binary conversion. All right, so let's say we want to do additions and subtractions in a different base. But before we actually do that, let's see an addition process, and we have to closely examine. You can do this in your head. You've been doing this all through your life, the addition process in decimals, right? So you don't even really have to think exactly what happens, right? You can just do it like instantaneously. So let's say you want to add two numbers. How would you add them? Let's say these are in decimal, base 10. You go again one digit at a time, go from the rightmost to the leftmost, right? 6 plus 2 is 8. Actually, let me see. Let's do 5. Okay. 6 plus 5 is 11, right? So you have 1 here and 1 carried out to the next digit, right? And then you add these 3 digits together, 4 plus 3 plus 1, that's 8, and then 6 plus 2 is 8. That's how you would add in decimal. You don't even have to think about it. You can just add, right? The idea is you're adding in terms of base 10. So every time your number exceeds 9, right? In this case, the number is 11. That's exceeded 9. So basically, you have the 1's position here, and the 10th position goes to the next digit to be added to the right. All right. Now, can I translate that same technique to base 8, for example? I want to add in base 8. How do I do this? Now, when you're doing, the rules are exactly the same. When you're doing it decimal, you're just adhering to the decimal rules, base 10 rules. So you're counting in base 10. When you're doing it in octal or base 8, you have to count in base 8, right? Because you're dealing with base 8. So let's say your numbers are again 2, 3, 5, 6, 4, 6. But this time these numbers are in base 8. How do I add them? So what will 6 plus 5 correspond to in base 8? Right? Now if I want to start counting in base 8, my numbers would go as 0, 1, 2, all the way to 7. What comes after 7 in base 8? That's correct. I need to use 2 digits now because the largest digit I can have for base 8 is 7. Then it will be 1, 0, 1, 1, 1, 2, and so on, 1, 7, then 2, 0, and so on. So that's how you would count in base 8. Okay. Now what will be 6 plus 5? So you can, again you count 6, 7, 1, 0, 1, 2, 1, 3, 1, 4, right? Oh, sorry, 6 plus 5 is 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, yeah, 1, 4. That will be 4 here, and 1 will be carried out to the next digit position. Now what will be 4 plus 3 is 7 plus 1. Yeah. 4 plus 3 is 7. 7 plus 1. 7 plus 1 is 1, 0. Right? So that will be 0. It will be 1. Here I have 6 plus 1 is 7. 7, 1, 0 plus 7 plus 2 will be 1, 0 plus 1, 0, 1, 1. Right? 6 plus 2 is 6 plus 1 is 7. 1, 0, 1, 1. Same rules, just have to count in that base, that's all. Just you have to keep track of the base, keep track of the count, and you get the right answer. So that's 1104 in base 8. Okay. We'll do one example in base 16. Again, same rules, just have to keep track of the base, keep track of the count. So let's say AE B6 plus, let's say 7, 3, B4. What would that be? So again, 6 plus 4 is A. What about B plus B? So you start with B, count until B, right? B, C, D, E, F. Again, B correspond to 11. So you need to do that. So I have, what do I have then? B plus B. So that's B. AC? Is that AC? Really? Let me check. So B correspond to value of 11. B correspond to value of 11. If I add them, I would get 22 in decimal. If I want to convert 22 into hexadecimal, again I'm trying to do it in hexadecimal, right? So 22 in hexadecimal will be what? B is 11. B is 11. 11 plus 11 is 22. 22 in hexadecimal will be 16 plus what is 22? 6, right? So this is 1, 6. Or let me put it this way. 1 times 16 plus 1 times plus 6 times 16 to the 0, right? Which will give me 1 6. Or you can just count it. So B, C, D, E, F. Okay. B, C, D, E, F. 1 0, 1 1, 1 2, 1 3, 1 4, 1 5, and 1 6. Right. So I counted 11. So that's 1 6. So either way, it is the same thing. All right. So that's 6. That's 1. E plus 1 is F. What is F plus 3? It's F 1 0, 1 1, 1 2. So that's 2, 1. 7 plus 1 is 8. And then A plus 8. A, B, C, D, E, F 1 0, 1 1, 1 2. Right? So that's 1 2. And that will be the corresponding sum in hexadecimal. Again, same principle, there's nothing different. Just have to count in the right base, in the right way, corresponding to that base. After A to F, we proceed, so after A to F, so the way we count in hexadecimal will be 0, 1, 2, so on, A, B, F, so on F. Then it will be, because F is the largest digit, single digit you can have in hexadecimal. Now after F, I need to use 2 digits. So that will be 1 0, 1 1, 1 2, similar to what we have in decimal, right? 9 is the largest digit. After that will be 1 0 or 10 and so on. In this case, it's 1 0, 1 1, 1 2, 1 3, so on, 1 F, then it's going to be 2 0, and so on, 2 1, 2 2, 2 3. So that's how you would count in hexadecimal. Okay. So again, today's class was more into the basic stuff, something that you already must have seen this before, but more of a review of what has been done, what you already know. And in the next class, we'll continue the discussion a little bit more, and like doing subtractions, and then we'll also look at some important concepts that you may not have seen before in the next class in the number systems. Okay. With that, any questions so far?
Excuse me. Is there any reading chapters you recommend, or?
So there should be
really have to.
the very first chapter. I think it's section 1.1 in the textbook should have this information.
Yes, I read it till like 1.4 now.
Okay.
I mean, everything is kind of similar to what you just said.
Okay.
It's literally the same.
Yeah, exactly. So yeah, so for additional reference, you can always go back to the textbook. Yeah.
Okay, thank you.
Mm-hmm. Any other questions? If not, then will you be assigning homework? Yes, absolutely right. I will be assigning the homework. You'll be seeing the homework today, okay, as a file where you have the questions and all typed out. So you don't have to, again, you don't have to go back to the textbook. So all my homeworks will be typed out. So, yeah. Okay. So let me